To complete a lab assignment, do every task in the lab report outline. There is one-to-one matching between the list of tasks and the lab guide app items. Part Introduction is a background review about the concept of signals, which are what the circuits of this lab are designed for, that is, amplifiers to amplify signals. If you have taken or are taking a course on signal analysis, you may be quite familiar with the materials, thus, treat them as a refresher. In this lab, we will use op-amp integrated circuit chips, which need positive and negative voltage supplies. How do we get negative voltages? Voltage is always relative with each other. Swap two terminals of a voltmeter that measures, say a battery, we will get an opposite sign value. If there are several independent source voltages, one can join them together to add, subtract, or make any combination thereof. One can choose an arbitrary node as the 0-volt reference to create new voltage values. Below is an example. With four 1.5 volt batteries, one can make 0 and 6 volt, or minus 3 volt, 0 volt, and plus 3 volts. With the BK power supply, one can additively connect the two independent supplies and connect their joined node, which is in the middle, to the chassis ground. Then, one side will provide a positive voltage and the other side, negative voltage. The color coding scheme is helpful to reduce risk of errors. The green color binding post on the board matches with the green color banana connector on the BK power supply, which serves as the ground. It is the same ground green color convention in household electrical wiring. The breadboard red and black binding posts respectively match with their counterparts on the BK. The most common cause of burnt op amps is erroneous power connection to the board. Indistinguishable, or inconsistent color coding of the wires is an accident waiting to happen, and invariably so. Consistent color coding scheme like this case can help reduce this risk. Alternatively, and actually more conveniently and recommended, two 12-volt AC-DC adapters, common in household electronics, can be used for this purpose. They can provide plus-minus 12 volt by connecting the positive terminal of one to the negative of the other, which will be the ground for the op-amp. Using the BK power supply has the risk of accidental touching of the knob, or incorrect setting. Sometimes, a user connects an off-state BK power supply to the breadboard and flip the power switch without checking the voltage knob settings. If the settings have excessive voltages, like 25 volt left by the previous user, damages to the op-amp will happen, and did happen in the lab. Fixed 12-volt supplies have less risk. If recycled from discarded electronics, the end-round connector can be cut, the wires can be split-stripped, and a marking scheme as shown can also help. Describe in the lab report your plan of how to power the op-amps in this lab for and beyond. If you don't have the type of connector adapter for a round jack to a pair of split bare wires, and have to do wire stripping of old AD-DC adapters, do a simple tagging on the wire as shown. Students had their op-amp burnt live on Zoom because they were confident of their memories of wire polarities, even though all the wires had the same color. Bob is building his house. He is considering the wiring of the house, electrical, cables for TV and internet. He observes electrical cord that is 20 cents a foot, and cable TV cord $1.38 a foot. On the open ends, they look comparable. Both have 3 copper conductors of similar size. He was wondering whether he should save using the electrical cord instead of the cable TV cord. In this lab, we will use a kind of electrical cable that we didn't use before. There is a reason. Consider the example whether Bob should try to save money using less expensive electrical cord or coaxial cable for his internet and video services. The two types of cables are both made with copper conductors and look similar, but they could not be any more different in terms of transmission properties, the properties of carrying electrical AC signals. At close-up, the geometrical configurations of the conductors are different for the two types of cables. The coaxial cable is called as such, because the conductors form a cylindrical geometry with the same axis. The conductors of the electrical cords are simply in parallel side by side. As it turns out, at any moment, the voltage of an AC electrical signal is not the same everywhere, but varies versus location. This is known as a wave phenomenon. As an AC signal wave travels over a cable, its amplitude decreases over distance. Illustrated here are the amplitudes of 1 GHz internet signal carrier wave over 25 feet of coaxial cable, top, and common electrical cord, bottom. If Bob used electrical cord instead of coaxial cable, he will have no internet and no digital TV because the signal from the ISP would disappear within several feet at the house entry node. In this lab, we will consider a very fundamental and important concept. The concept of finite time response. What does it mean? In the follow, we will go through a series of examples for amusement that elucidate this notion. Consider two lamps. A nearby lamp and a faraway lamp, both are connected with the same copper electrical cord, tapped in the parallel configuration. The electrical cord is suddenly plugged in. Do both lamps light up instantaneously at the same time? No. It takes a finite amount of time for the AC power signal to travel from the outlet to reach the lamps. Consider a lightning strike, destroying a power transformer station. Does a house lose power instantaneously at time t equals 0? Do a nearby house along the transmission line, and a faraway house down the line both lose power immediately at the same time? The same answer as the previous. No. There is a time delay. The nearby house will lose power first. Shortly after the lightning, the faraway house will experience power loss a little later. The local neighborhood central office of an internet service provider suffers a catastrophic failure. Will your house internet service stop instantaneously? The same answer. Whatever information bits already on the way to your house will continue to do so. The speeds of AC signals in coaxial cables or optical fiber are very well known, and the latency of service disruption can be calculated accurately. Time is money. Saving time is saving money. How much is saving 0.03 of a second, that is 3 milliseconds, worth? The data connection between the New York Stock Exchange and the Chicago Board of Option Exchange was based on an old optical fiber path that had been laid along the old AT&T copper cable telephone routes connecting cities and small towns from New York to Chicago. The zigzag optical fiber is longer than the straight line between the two cities, and the various node connections add delay in transmission. Light travels in glass optical fiber at the speed of 200,000 km per second, and somewhat faster in holy fibers. Hence, the financial industry wished to have a shorter optical fiber network, with fewer slow repeaters, to save time for a lower data latency between the two exchanges. The upgraded optical fiber network shaved the latency from 16 to 13 millisecond, that is, 3 millisecond faster. Saving 3 millisecond was deemed to be worth $300 million for the price of the network. In the world of high-frequency trading where securities are bought and sold on the microsecond scale, millisecond appears to be a large time lag indeed. And that is not the end of the story. Traveling 200,000 km per second between New York and Chicago in a conformal straight line along the Earth's surface curvature is still too slow for the world of supercloud computing high-frequency trading. So, old-fashioned microwave transmission in air at 300,000 km per second was back. But microwave carriers cannot offer the reliability, security, and massive bandwidth of light carriers, and hollow core fibers which offer the transmission speed closer to the nature speed limit of 300,000 km per second are in favor. If high-frequency traders were present at the birth of the universe, they might have petitioned the value of 1 over square root of epsilon naught times mu naught to be far beyond 300,000 km per second as we presently know it. In March 2020, Voyager 2 was 11 billion miles from Earth. It was still transmitting data to Earth. If, hypothetically, it had suddenly been destroyed by an interstellar asteroid, would we on Earth have known instantaneously something wrong the moment it were hit by the asteroid? Not really. It takes over 8 minutes for sunlight to reach Earth. It would take 16 hours 20 minutes for Voyager signal to reach Earth in March 2020. In September 14, 2015, people observed for the first time evidence of gravitational waves, the result of two black holes merging. When did the two black holes merge? It happened about 1.3 billion years ago, at a distance of 1.3 billion light-years. Let's get down to Earth. Consider all the cases above. Is there such a thing as an instantaneous response to a stimulus? Is there such a thing as instant consequence of a causal event? There is no such a thing. It means every cause and consequence has a finite time response. It means it takes time for something to respond to a stimulus. Another way to say it is this: there is no such a thing as instantaneity in an event with causality, i.e., cause and effect. There is always a delay because of the finite propagation speed and response time. If the event has spatial extent, no matter how small, there is always a time delay that cannot be faster than the propagation time with a speed that cannot exceeds the fundamental nature speed limit. As a side note, quantum entanglement, for that matter, is not a causal event. What does all of this have to do with lab assignment 4, which is about the op-amp? It has to do with a key aspect of this lab, the response of the op-amp. But first, let's take a look at the op-amp. It is a complex semiconductor circuit. This course is not about semiconductor devices and hence, it is not concerned of its details. The interest is only to use it, the way a car can be very complex, but a user is interested in only how to drive it. The follow is not needed. One can fast forward to the part in which the op-amp is treated as a voltage-dependent source in the circuit theory, and how it will be tested in this lab 4 assignment. For those who are curious and interested, or those who already know the materials but wish a quick review, proceed next for a background of the op-amp high-gain amplifier model. Again, it is not needed to do the lab work, hence, if you feel lost, just skip to the part discussing the op-amp linear voltage-dependent source. To the user, the op-amp behavior is remarkably simple, unlike its appearance of internal complexity, which can be ignored and replaced by a simple mathematical function. The output Vout is a linear function of the difference of the two inputs, which is multiplied by a constant, denoted as A sub OL in the equation. A plot of this function is shown on the right. It is just a straight line. The horizontal axis, the input, is in the sub-millivolt range, while the output is in the 10-volt range. This is because the linear coefficient, A sub OL, also called open-loop gain, is intentionally designed to be very large, like 100,000 to 10 million, in other words, it represents a very high gain amplifier. An op-amp cannot output a voltage higher than its supply voltage, hence, the high gain output saturates. Most op-amp applications are not intended to have a saturate output, which means the operational range of the two input terminal voltage difference must be very small, in the few tens of microvolt range. How can such small voltages be controlled? There is a method to do that, which is negative feedback, and precisely the reason the op-amp is designed with such a high gain is because it is not intended to be used as is, but only with negative feedback that will be considered next. Consider this mechanical analogy. A mechanical arm is held around a pivot axis, shown as the red dot. An external force, green arrow, can cause it deviates from the rest position. The stronger the input force is, the larger is the swing. One way to reduce the swing is to apply a counter force at the other swinging end. However, here, to illustrate the concept of negative feedback, another approach is taken. A control bar rigidly held parallel to the axis by a rail system, but allowed to freely move up and down, is attached to the end of the arm with a pivot. Then, a slider is attached to the other end. A spring is attached from the control bar slider to the input end of the arm. The spring exerts a force that partially negates the input force. This is negative feedback. The system with negative feedback on the right has smaller swing than the one without on the left. The strength of the feedback can be externally controlled by using springs with different coefficients. Strong spring provides stronger negative feedback as illustrated next. The analogy with the op-amp is this: the red pivot point of the mechanical arm has a certain torsional strength that is not controllable. But the external spring can be chosen. If the input force is in turn controlled by another input lever arm coupled to this arm with an input spring, it can be shown that, just like the negative feedback op-amp voltage amplifier, the ratio of the output angle versus that of the input lever is mostly dependent on the ratio of the two spring coefficients. If the torsional coefficient of the red pivot point is very weak, just like the op-amp infinite open loop gain. For the sake of completeness and the mechanical purist, the spring is three-dimensional and hence, it looks circular sideways when the two bars are parallel, and the spring is at rest. There is no vertical force between the bars. Apply the above analogy to the op-amp. First, there is only one relevant input variable, the difference between the two inputs, X non-inverting and X inverting. Hence one of the two can be set to be the reference ground. Here, the non-inverting input will be the ground. The equation become quite simple: V out is minus inverting input multiplied by the open loop gain, because X non-inverting is 0. Next, like the mechanical arm that lifts a lever for negative feedback, the output is connected to inverting terminal. How much feedback, like the coil in the mechanical model, can be controlled with a resistor, which is the feedback resistor. If the resistance is infinite, it is the same as without negative feedback. Hence, the lower the feedback resistance, the stronger is the negative feedback. In this sense, the feedback resistor is like the coil in the mechanical model. Lower resistance is like a stronger coil. The feedback current, IFB, is equivalent with the feedback force on the mechanical arm. The lower the feedback resistance is, the higher is the feedback current, like the stronger is the feedback force of the lever. The negative feedback current can now negate the input signal current, like the coil force negates the input force. Here, the situation depends where the input signal current comes from. If the current comes from a photodiode like the transimpedance amplifier circuit in this lab, then, the signal current is directly dependent on the photodiode performance. For a sneak preview of this part of the lab, the video in the lower right illustrates the op-amp output, the blue trace, responding to the input from the photodiode signal current that senses the fast blinking light output from an LED desk lamp. If the input signal is a voltage, like the sound signal from a microphone or just any voltage signal, then the signal is coupled to an input resistor R1 to convert it to signal current I1. Now the effect of the feedback current can be calculated. To apply Kirchhoff's current law at the X inverting node, the internal impedance between the two op-amp terminals, the inverting and non-inverting, is needed and is denoted as Z0. Although it is very large, in the megaohm or much higher range, and often approximated as infinite, the term is kept for the sake of principle. Then the current conservation at X inverting node gives the equation to calculate the negative feedback effect on V out. There are two equations for two unknown node voltages, X inverting node and V out node. The system of two linear equations is trivial, but it is tedious to go through it algebraically. For better amusement, and those who wish to learn how to use Mathematica to do the skullduggery work of algebra, can type along the codes as shown. The solutions, however, is a bit busy looking. A little algebraic rearrangement can give a more meaningful expression of V out, which contains two expressions. The expression on the rightmost is a fraction that approaches to 1 as AAOL, the open loop gain coefficient approaches to infinity. The reason for the large open loop gain is now obvious. Output V out is a linear function of input V in, but this linear coefficient depends only on the externally controllable parameters, R feedback and R1, completely independent from whatever inside the op-amp. It means that as long as the open loop gain is very large, it doesn't have to have any particular value and the op-amp manufacturing variation hardly matters. This is exactly what is desired of a stable amplifier, and negative feedback is the mathematical principle behind this stability. More generally, however, real physical devices do not operate like an ideal mathematical model. Open-loop gain is not infinite if the input signal varies too fast, that is, having high frequencies. Thus, it is more appropriate to express V out as a function of input signal frequency omega. At high frequency, AAOL drops to as low as 1, that is, no amplification. Then, the internal physical properties of the op-amp, both AAOL and impedance Z0, with their phase frequency responses, are relevant to the output. Hence, we will see later on that there is an upper limit of signal frequency that an op-amp circuit such as this one, can remain useful for applications. As a side note, negative feedback and feedback in general are a fundamental principle pervasive and ubiquitous all around us. Even a flush tank uses negative feedback. The higher water level, the smaller is the valve aperture, which is eventually shut off, preventing overflow. From household to industrial, feedback mechanisms are used everywhere. For example, even highly simple things like the ground fault circuit interrupter uses negative feedback. The household thermostat also uses negative feedback control in a binary discrete mode, on or off, to maintain the temperature within a certain range. More generally, various feedback designs, with PID being one of the most common, are used everywhere for numerous applications. In fact, wherever there is a need of control, there is feedback, often negative feedback for stability. Our body, all biological systems, and in ecology, feedback loops are essential. In economic and finance, feedback, whether by the market force, that is the invisible hand of a free economy, or human society regulatory controls, are essential. A most basic negative feedback in economic is the price elasticity curve, for example. Raising the price will raise profit, but demands will fall, and hence it is a negative feedback to price changes. Even human intervention is sometime needed. For example, there is a massive change in financial regulations to provide control and feedback after the runaway credit default swap financial crisis in 2008. Major stock exchanges have mechanisms such as the circuit breaker when trading is excessively volatile, like an AC system would turn on when the temperature is too hot. Law and justice systems have always managed punishments as negative feedbacks to human social behaviors ever since the formation of complex societies. The emergence of social media in modern time expose an individual to an even wider social circle than the traditional family and friends, and hence, make an individual even more susceptible to social influences via negative or positive feedbacks that may affect one's mental health and behaviors. Back to technology, for the sake of history, it is worthwhile to mention that James Watt's fly-ball governor was a crucial technology responsible for making the steam engine the transformative driver of the first industrial revolution. Lastly, and also for the sake of history, the origin of negative feedback with op-amp can be traced back to the early days of vacuum tube amplifiers, when Harold Black developed the technique of negative feedback to reduce the amplifier distortion and enhance the stability. The digression on a review of the op-amp is done. Now we are back to the use of op-amp as a linear dependent voltage source, which is a main topic of this lab. There is a slight notation difference between the previous discussion and what follows. It is worthwhile to make a note of it. In this model, an input voltage Vx will result in an output voltage Vs. S stands for source, because it is a voltage source, whose value depends on Vx linearly with a factor of minus the ratio of two resistances, a resistance called feedback, and resistance R1, which is the input resistance of Vx. This model is quite remarkable in simplicity, given the complexity of the op-amp and the negative feedback. However, using the car analogy, a car technology can be very complex, but to the user, it is more relevant to test its performance. Let's choose feedback resistance to be 2 kΩ, and input resistance R1 1 kΩ. Then by the simple formula, V source output is simple minus 2 times of Vx. As an example, suppose a set of voltage values as shown are applied to Vx, then output Vs should have corresponding values as shown, which is a factor of minus 2 times Vx. It is a simple linear relationship. Now is the time to make relevant all the discussion above. What if Vx is an AC signals? Can Vx, a time-dependent function Vx of t, be substituted for Vx, and likewise for Vs? Can this be correct? Apply the discussion above, this cannot be correct. The reason is that it says that Vs is exactly proportional to Vx at all time, which means it is instantaneous with respect to Vx. This cannot be true. The examples above about the latency of cause and effect tell us not to make such a generalization from DC to AC blindly. Hence, this model that was considered correct above is now cannot be correct, if Vx is a function of time. But it is known that this simple model is correct as long as Vx is constant, that is, a DC voltage. How can a formula be correct if it is constant, but not if it changes with time? How do we resolve this paradox? Applying the method empirical learning, we can simply conduct an experiment to find out what will happen. This is what will be done in part A, next, but it doesn't hurt to preview a result that was already shown in part introduction. A very simple test is to use Vx with very sudden change. Mathematically, this is also known as a Heaviside step function. We know that the model works whenever input Vx is constant. Hence, it works before the step, and it should work long after the step. But what will happen in between, that is at the step? What will Vs do? One thing certain is that Vs cannot be instantaneous with respect to Vx per the discussion above. The way to know the detailed behavior is to do an experiment. The AD2 was used to do the measurement. The signal output function was set up to input into the op-amp circuit. Vx is a step function as shown. Output Vs shows that it cannot jump instantly from one level to the next like Vx, but ramp slowly to the next level. It is not, and cannot be proportional to Vx instantaneously at the transition time. In other words, the voltage-dependent source model works at a time before, and long after, but not at the step. The rate of ramping, in unit of volt per second, is called the slew rate and is a property of a specific op-amp. Some op-amps have high slew rates, some have low. The higher its slew rate, the likely more expensive is the op-amp. The experiment shows what follows when the step change of Vx gets more and more frequently. When Vx changes so fast, the output Vs waveform no longer looks anything close to the Vx input. Hence, the voltage-dependent source model works, but only below a certain frequency limit. Like the car analogy in the introduction, how well does an op-amp respond to high-frequency input is a figure of merit of the op-amp performance, like a car acceleration, and this lab is a study of this frequency response concept. This step is about the practical use of transmission cables. In previous lab and from common experience, one needs no introduction of simple electrical cords. But from here on, we start using high-frequency transmission cables for AC signals. Strictly speaking, the frequency ranges and transmission distances of the AC signals in the remaining lab assignments are quite small and household electrical cords can be used. For the educational purpose, however, it is important to practice with high-frequency transmission technologies. We revisit the topic of signal transmission. But here, it will not be about the theoretical concept, it is about the technology of transmission cables. There are different types of cables to conduct, or transmit electromagnetic signals of different frequency ranges. Bob should not use the electrical cord, because it does not have sufficient bandwidth for the high-speed internet and digital TV electromagnetic signals. He should use the coaxial cable, which has a proper bandwidth for those signals. Why does the transmission of AC signals have to be so complicated? Why can't we use a one-size-fits-all technology? It has to do with both the nature of the wave phenomenon in general and the electromagnetic wave in particular. Let's have a digression to consider this matter. There are different types of waves. Water wave. Air pressure wave, which is essential to transmit our speech communications. And the most ubiquitous wave, the electromagnetic wave. A remarkable aspect of the electromagnetic wave is the diverse properties of waves of different frequencies. From the technology viewpoint, the electromagnetic wave, at least for over a century, is most commonly associated with telecommunications. Although its history is dated further back in the early 19th century, as both the wired telegraph and telephone are also electromagnetic in nature, the wireless communication capability of the electromagnetic wave, first demonstrated by Marconi, sparked a mini-industrial revolution in the early 20th century. The subsequent development of the radio music box and broadcasting launched a massive industrial development of the electromagnetic technology that, with the exception of the development of the radar during World War II, has been driven principally and almost exclusively by the telecommunication industry. The op-amp was developed as a solid-state infinite-gain amplifier to substitute the vacuum tube amplifiers that were noisy and unstable for telecommunication applications, which led to the development of negative feedback, which is the circuit of this lab assignment. Harold Black's work in developing negative feedback amplifier was done at the old Bell Labs, the research arm of American Telephone and Telegraph, founded as the Bell Phone Company by Alexander Graham Bell in the late 19th century. It was like a Google of its days. Virtually all the main topics you are learning in circuit theory, and this circuit analysis lab, were the results of technological research and development driven by the telecommunication industry of the 20th century. This lab assignment for negative feedback op-amp circuits is a historical legacy of that development. To the majority of lay public, electromagnetic wave communications are best known in the frequency range from megahertz to tens of gigahertz, because of applications such as Wi-Fi, Bluetooth, 4G or 5G networks. In addition, all are familiar with the electromagnetic wave for broadcast like radio and TV. Not to be overlooked is the spectral range that, besides telecommunications, is even more intimate and essential to the human experience, the electromagnetic waves in the optical range, which includes what known as the visible spectrum. It is an essential component of human and animal visions. The reason is because it is the peak spectrum of the sun radiation onto Earth, which fortuitously coincides with the relevant energy range of biological molecules such as bacteriodopsin, chlorophyll, and life evolves to adapt. Its energy feeds all life on Earth, the plants, the food animals eat, the energy in the fossilized fuels used in our life. It heats the Earth, drives the winds, evaporates water for rains, generates all forms of weather on Earth. Back to the consideration of wave propagation and transmission. The technologies are complicated because the electromagnetic waves in telecommunication applications are so widely diverse. The nature of a wave is to spread out as wide as possible, thereby losing more and more its power per unit area the further it spreads, just like the ripple amplitude becomes smaller with larger wave circles. A wave maintains its power in a tight area only if it is confined by some structure. It is simple for certain type of waves, such as sound waves. With a simple tube, a person can hear from the other as if the message was whispered into the ear. For the electromagnetic wave, it has such a wide range of behaviors in interacting with materials such as metals and dielectrics as a function of its frequency, hence the various structures designed to confine and transmit the wave are necessarily diverse over the widely different frequency ranges. In this lab, we actually use coaxial cables for technologically the lowest frequency range, a few gigahertz maximum. If you work with micro or millimeter waves in communications or radars, the transmission medium technologies are different, from semi-rigid coax to waveguides to various microcircuits. And for the optical frequency, optical fibers and waveguide photonic circuits are essential technologies for the internet or the metaverse data traffic. Hence, one-size-fits-all technology is not realistic. An analogy of the diverse transmission technologies for different frequency ranges is this. The lab work in this step aims for practical, manual experience. In the lab, you will start handling coaxial cables and practicing disconnect them to and from instruments. Gain manual familiarity with the connector type known as BNC, which stands for British Naval Connector. Use structures such as elbows, T-splitters, 50 ohm or short terminators, and attenuators if available. If you are at home, please check if you have home video cables, which are of the type RG59, similar to RG58. If you are completely home-based and cannot come to the lab, your assignment is to take a picture of your handling of coax cables if you have them. However, if your home cabling and internet service uses flexible yellow or orange noodle-like strands, they are optical fibers, and you don't have to worry about handling the coax. This last step is about doing hands-on work with real instruments. That is, generating waveforms with the signal generator and measuring them with the oscilloscope. In particular, practicing basic waveform measurements with a D2 is beneficial both educationally as well as for Lab 5 and Lab 6. Hence, it is worthwhile to invest a little effort to get deeper into waveform measurement techniques with the AD2, and this step will be treated on its own in a separate video.